Here we go. The magnetic dipole moment of a loop of current. I'll be honest, this one's a little bit tricky. So this is part of my series of Python examples for physics educators to use in their introductory physics courses. I'm working through the introductory course and doing a whole bunch of activities that you could possibly implement in a lab or a lecture course. Now, maybe you're also a student, and I welcome you. That's cool too. I personally am a student of physics. I'm always learning things. And so I've been working through the whole course. I'm in the second semester doing electricity and magnetism. And in the last video, I did the magnetic field due to a long wire. Now I want to do a loop of wire. Now, analytically, this is actually a pretty easy thing to calculate the magnetic field due to a loop of wire along the axis of that loop. Numerically, it's not quite as simple. There's some tricks going on here. But we do get something different. In the analytical case, we only get the magnetic field on this axis. But if we do this numerically, we can find the magnetic field anywhere. And what I want to show is, number one, that this does look like a dipole. So if I draw this from the side, there's my loop. The magnetic field looks like this. Well, your standard dipole field, these are the field lines. So over here, the magnetic field's going that way, that way, that way. I want to show that. Number two, I want to show that the magnetic field along the axis decreases as 1 over r cubed, just like the electric field dipole. There's a video on the calculating the electric field due to a dipole, and that's much easier because you have these 2 point charges. You don't have this loop. Okay, so here's the answer that we want, the analytical answer. I'm going to get to this in a second, but how do we do this numerically? Well, this is the magnetic field due to a moving charge. So it depends on this magnetic constant. QV is the electric charge, V is the vector velocity, R hat is the unit vector in the direction of the observation location. So let's get that out of the way. So suppose I have this ring right here. I'm going to switch over here to this, and then divide by R squared. If I have a wire, I really just replace QV with I delta L, where I is electric current, and delta L is the vector piece, the direction of the path. Now remember, in the last video, for the magnetic field due to a long wire, delta L was a constant, right? It just kept going in the y direction. But here it's not. As I move around the circle, delta L changes. Okay, now what about this R hat thing? And that only gives me a part of the magnetic field, right? Because each piece has a different delta L, so I have to calculate all the pieces separately. Okay, the R. So imagine that I break this ring into a finite number of straight currents, delta L. I can find the vector location of each piece. I'll call that RP. I have the vector location of the observation location where I want to find the magnetic field. I'll call that RO. And then R is a vector from the piece to the point. So that R is RO minus RP. And as I move around the ring, RO is constant, but RP changes, so that makes R change. So I'm going to have to do that. I'm going to have to break that into pieces. Now, we do have a problem here. Okay, let's go ahead and give some parameters. I don't even remember. Let's say the radius of the circle, R, is 0.01. Let's say R0, the magnitude is 0.05. I is 0.2. I'm just picking something. That's all I need, I think. And the magnetic constant, that's 1 times 10 to the negative 7th, this right here. So I need to break this into pieces. And let's say I break it into 8 pieces. I can do that, right? One of the ways I'm going to do that is to say the piece location is going to depend on some theta. So RP is going to be R times the vector cosine theta, sine theta, 0. Actually, it's not going to be X. I want to put this in the XZ plane. So I'll just put this as the 0 over here. That way I can see it better from the side. But then as I change theta, I'll just change theta and I'll find my new piece. And that's all cool and everything. But what about delta L? In the past, like I said, delta L was constant, but it's not constant. So here I'm going to use a trick. I'm going to say this. I'm going to write it down and then I'm going to say it. Delta L equals, I'm going to write it out as 2 pi r over n. N is the number of pieces I break it into. So this is the length around the whole thing. I'm going to break the length into pieces. And then I'm going to say, let's say RP hat cross Z hat. That's my trick, the cross product. Because if I have RP is right there, and let's say Z is out of the board, RP, well, let's do this negative in this case. RP cross Z would be that way, using the right-hand rule, right? So, and then as I move RP over here, delta L is always going to be perpendicular to RP and Z, so it will give me the correct direction for that by using the cross product. And that's a little trick, right? Otherwise, you're going to be really have a hard time of finding all those delta L vectors. Okay, so one other thing, what I'm going to do, in fact, is to break this ring into a list of pieces, and that way I can go back through and calculate the magnetic field due to each piece, but I'll need that delta L up here in that calculation. I know this is complicated, okay, but we're going to win. We're not going to fail. We're going to win. We're not going to let this thing defeat us. We're going to make it. It's going to be awesome. I'll admit, I already did make this and I made a mistake, so I'm redoing it. Okay, so this is what we expect to see. This is the magnetic field due to loop on the axis, 2i pi r squared. Z is the distance along the axis squared. And this is, if you're far enough away, you can approximate it this way. And then if you have, if you want to turn this into this, since this is Z squared, this pi r squared is the area. And so we can write this as mu naught over 4 pi, the constant, 2 mu over r cubed. And this looks like the electric field due to a dipole too. There's a 2 if you're on the axis. There's not a 2 if you're not on the axis. But it gives the field on the perpendicular axis and the vertical and the along the axis. I think we're ready. Okay, let's jump over to Python. We got a lot of work to do. Okay, and I might make a mistake, but mistakes are just part of the stuff that happens, right? When we're on our way to a solution, and I might knock my light over. Okay, so I'm switching to computer. So this is GlowScript vPython, or Web vPython now it's called, just in case you're worried. You can do this with Jupyter notebooks. One of the things with the GlowScript is it has like these visual elements that are really nice and useful. So and you don't have to install anything. It just runs in a web page, and I think that's awesome. Okay, so let's just put down my constants here first. I'm going to call this Km equals 1 times 10 to the negative 7th. That is my mu naught over 4 pi, because I don't want to write mu naught over 4 pi. I need R equals 0.01. Let's say RRO. That's my distance along the axis, 0.05. And then I have I is, what did I say it was? 0.2. Let me check my notes here because I don't make a mistake. Now the other thing I need is N. N is going to be the number of pieces. I'm gonna start off with 8. And with that, I also want to start, remember, I want to use this angle theta. I want to move theta around. So I'm going to say theta equals 0. D theta equals 2 times pi divided by n. I made this mistake before. Okay, so if I want to increase theta each time, that's the theta increment size to go all the way around the circle. I did this before. I put theta over n, and that's not right, because that would be 0 divided by 8, which is 0, and it went into infinite loop, and I felt really dumb. But like I said, you just make mistakes sometimes. It's okay to make mistakes. I mean, we don't do things perfect the first time always. Let's see, what else do I need? I need, that's it. Okay, now I'm going to make my list. So what I want to do is to go around, I'm going to start off with a sphere. Let's not make the list. Just make 8 points and make sure that we have everything working. So I'm going to say while theta is less than 2 times pi, the first thing I'm going to do is calculate a temporary r. I'm going to say rp temp. It's going to be equal to r, the radius of the circle, right, times the vector 0 cosine theta sine theta. Now I'm going to put a sphere there. So I'm not going to give it a name. I'm just going to say position equals RPT, radius equals 0.002. And then I'm going to increase theta. And that's that. Okay, let's see if this runs. Okay, there you go. They're a little bit big. Let's put this point. It doesn't really matter. But there's my 8 points in a circle on the YZ axis, the YZ plane. And that's what I want. Okay, so that looks like it's working. What I want to do is, instead of making spheres, I want to make arrows to represent the delta L vector. Okay, so let's do this. I already said what I wanted that to be. So let's see, DL temp. Let's go up here. Ring equals an empty list. I do have a tutorial down below somewhere. I can't remember where. If you look at the playlist for this whole series, somewhere down below there is a playlist for. Let's see. Wait 1 second. A playlist for lists, so you can figure out how to do that. I'm not going to go over it right now. I just assume that if you want to look at that, you can. So let's make this temporary vector dl t. It's going to be equal to the total length, which I said was going to be 2 times pi times r. That's the 2 pi r. That's the length around. But I need to divide that by n, right? That's the length of one piece. So divide by n. Times, that's going to be the length, that is the length of my piece. Now I'm going to take the cross product, let's do it backwards, z hat, which is going to be the vector 0, 0, 1, and, cross product is built into Python, in case you can't see that. And RPT hat, which is norm RPT. Yeah. Okay, so now I'm going to say ring equals ring, plus I'm going to add an arrow, an actual arrow into the list. So I'm going to say arrow, the position is going to be RPT, the axis is going to be equal to DLT, and let's just leave it as white. Okay, I'm not going to put the spheres in there because I just want the, so let's just delete that. Okay, let's see if this works. No. It did not work. That's weird. Wait, 1, 2, 3, 4, 5, 6. I don't even have all the vectors. There's only 6. I think 2 of them are 0. Okay. I made a mistake with the cross product. It is Z cross RT. Oh, no? Okay, so RP is in the X, the YZ plane. Oh, this is should be X. Yeah, I forgot. Okay. Okay, boom. I mean, that's artistic. Sometimes art comes out of this, and that is art right there. Okay, if you want, you could go through and add up the length of all those things to show that they are indeed the circumference of the circle. You could increase this. I like to do multiples of 8 because they fit in there nicely. And you'll see here that the arrows get smaller, and that's it. Okay, so I'm pretty pumped up about that. Let's change it back to 8 for right now. Okay, so all that did was make my list. Now I need to go down here. I need my observation location, a vector. So let's do that. RO equals vector. It was on the x-axis, so it's RRO 0, 0. And the reason I do this, I have that scalar value up there, RRO, so I can change that. I don't have to worry about changing all this other stuff. Now I want to go through the list and calculate the vector R for each element. And I want to calculate the contribution of the magnetic field due to that. And then I want to add it to the total magnetic field, which I have not done because I don't have a total magnetic field. So I need to do that. B equals vector 0, 0, 0. If I want to find the magnetic field and add them up, I need to start somewhere. So this is my starting somewhere. Okay. I'm still kind of excited about that picture. I just like that picture. It looks cool. It'd make a good logo or something, don't you think? Okay, so now I'm going to use a nice list trick. I'm going to say this. For, let's call this DL in ring. So if I do it this way, it goes through the list of ring and it calls each element DL. I don't have to have an indices that I could go through it or anything. Let's just do this. Print DL.pos. It's going to go through the ring and print out all the positions of the rings, of the pieces, just so you can see how that works. So that's kind of cool. Okay, but I don't want to print it. What I want to do is, number one, is to calculate the vector R. So R is going to be the piece location, which I just had. It's going to be the observation location, RO, minus DL.pos. Now I can calculate the contribution of the magnetic field, dB equals Km, that's the mu naught over 4 pi, times I times the cross product of DL cross R. So it's going to be DL is actually DL dot axis, right? Because up here when I made this, the axis for that vector is this little piece DLT. So this is kind of weird. I'm actually using the visual attributes of the vector, which is, I don't even have to scale it because it is the length. I'm using that as my DL. It is DL. I'm not using it as DL. It is DL. Cross norm R, and then I need to divide that by mag R squared. Now I need to take that contribution of the magnetic field and add it to the total. So B equals B plus dB, and that should be it. Yeah. So now let's just print it out. Print B in equals B Tesla. Let's just see if it works. I never even saved this. That's living on the edge right there. Okay, so let's save this. B due to loop next try, because I tried this before. Okay, and I run it. And you'll notice here that it gives me a vector in the x direction, some y and z components too, but we know that the magnetic field should be in the, oh, I guess it's that way. Wait, no, it's that way. My video is backwards. It should be along the x-axis, and you see it's not, but it is, right? 10 to the negative 23 versus 10 to the negative 8. I mean, that's all cool. Let's calculate the theoretical version. So let's say B calc, BC, is going to be Km times, I'm looking at my equation right here. Let's see, I got it right here. 2 times I times pi times R squared divided by z squared plus r squared to the 3/2. So it's going to be divided by z squared, which is RRO squared, plus r squared raised to the 3/2 power. And let's print that out. BC, this is a calculated version. BC Tesla. And now let's do the other version, which is B approximation. And that's going to be Km times 2 times I divided by R. No, that's 2 times pi, 2I pi R squared divided by z cubed, so that's RRO cubed, and print that one out. BA equals BA Tesla. Okay, let's run this and see what happens. Okay, so I get, oh, that looks pretty good. 9, even, look, that's with 8 pieces. With 8 pieces, I got the same thing. I can't believe that's the same thing. It's a little bit different for the approximation, but that's fine. Okay, now we can go up here and I could change this to 32 pieces. And it still works and everything is awesome. Okay. Now, what I want to do. I want to create a plot of the magnetic field vector around that region so we can see that it is a dipole. And then after that, I want to make a graph of the magnetic field as a function of r along the axis. Yeah, I know we're already at 20 minutes, but if it's good physics, I mean, we should stick around and keep doing this, right? We shouldn't stop. We should keep going. I want to keep going. If you want to pause the video and come back later, if you want to stop, I support that decision of you, okay? I want you to be happy. Let's see. So what I want to do first is to make this a function that calculates the magnetic field, because I want to calculate the magnetic field at different locations. So let's call this, I'm just going to call this B, which I know is a bad idea. I'm going to do it. So def B, and it's going to input, it's going to use that existing ring. I'm not going to make the ring in my function. I'm going to assume that ring R exists. And yes, you can do that. It's not always the best idea, but you know, life is full of things that are bad ideas that we do anyway. Okay, there, I've said it. So B, I need to input only RRO. I'm going to call this RRO. RRT for the temporary RTO. Yeah, that's my temporary observation location, and it is a vector. Okay, that's all I'm going to get in there. So then all this stuff is my calculation. It's not even that much. So I need to indent that. So BT, and I can't call that B. DL and ring, that works. R equal, I need RO. RO equals, no, that's just going to be RTO. So I'll just change this to RTO. It's a vector already. DB, this is going to be, that's fine. This is going to be BT, and then that's it. And then return BT, and then there's a space right there. There shouldn't be. Okay, so now down here in my B, all I have to do is change this to B, R, let's just call this vector RRO 0, 0. So that should work, right? I should get the same thing. All I did was shift all that into a function. And yeah, let's do it. Okay, it worked. Yes. Okay, now this magnitude of the magnetic field, 10 to the negative 8th, is really important. That's going to be used for this thing up here. I'll put it right here, B scale, right? Because if I want to draw a vector for the magnetic field, this is in spatial, this is a spatial arrow. It has spatial size. It has a length in meters. But the magnetic field is 10 to the negative 8th. So I need a scaling factor so I can make it look correctly. So I can call B scale equals, let's just put it at 1 times 10 to the 8th. Let's just try that and see what that looks like. So down here, I'm just going to draw an arrow once. So say, let's just call it an arrow. The position is going to be equal to RO, which is RTO, which is this RR vector RRO 0, 0. The axis is going to be equal to this. I'm going to copy it. It's going to be B scale times that. And then the color, let's make it yellow. Color equals color dot yellow. Let's just see if that one arrow works. And it didn't. See, this is why we try things. Missing right parentheses. I can fix that. Okay, so down here I have vector, arrow. I'm missing a vector. There's this arrow. Position, vector, B scale. Oh, I have an extra one right here. That should be times. No, that's right. That, I need an arrow, a parenthesis right here. Okay, way too big. Let's make it, where's my B scale? B scale 10 to the negative 10 to the 7th. Too big. 10 to the 6th. And you can do a better way of doing this, but there's nothing, there it is. Okay, let's do 10 to the 5th. Okay, so there we go. There's my arrow, there's my ring. We are all set to rock and roll here. Okay, we're gonna make another theta. I'm gonna call this alpha. Alpha is the angle in the XY plane to move around the step size. Again, I need another n. So let's make it 8 pieces. So I'm just gonna go down here. I'm gonna get rid of that arrow. Don't want it. And I'm gonna say n equals 8. Alpha equals 0. D alpha equals 2 times pi divided by n. And then I'm going to say while alpha is less than 2 times pi, alpha equals alpha plus d alpha plus. That's going to get me all around. And then what I want to do is to calculate the magnetic field of each piece and put an arrow there. So I'm just going to put an arrow. So I'm just going to say, oh no, I need another r. Let's call this r equals how far away, how big is my circle? Let's say it's at actually 0.03. So let's calculate RT2. That's my RO2. My new observation location. RR times the vector cosine alpha sine alpha 0. And remember, this is a circle in the XY plane, so that's how we want to do that. Now I'm going to make an arrow right there. I don't like being crunched down at the bottom. I'm going to make an arrow there, so I'm just going to I'm not even going to give it a name, arrow. I'm going to give it a position. Is RO2. I'm going to give it an axis. It's going to be equal to B scale times B of RO2. You see how easy that is? And the color is color dot yellow. And then I'm going to increase alpha and do it all over again. I feel like I made a mistake here, but if this works, I'm going to give myself a high five. There's a high five right there for you. That worked. My B scale is a little bit high. I want to make that a little bit smaller. But it worked. Let's make this at 5 times 10 to the 4th. Okay. There you go. There's the dipole field around a loop and with 8 pieces. And I'm really excited about that. I'm really excited. That looks really great. My ring's a little thin, but you could fix that. You could go and change the thickness of an arrow. I could also change this to 16 in order to make it a little bit bigger anyway. And there you go. Art. And one of the things with this, it always looks like it's not a circle because the arrows start at the end. So if you draw a circle around the beginning points, you can see it is indeed a circle. It looks like it's shifted. It's not shifted. Okay, so that is a dipole field. We could change, let's make this a little bit smaller. B scale at 2, and let's change this n to 16. Yeah. Okay. I mean, that's just great. Come on. No denying that that's great. Okay, now I'm going to make one more thing. I'm going to make a plot of the magnetic field as a function of distance along the axis. I'm going to plot it 3 ways. I guess I should also, I never down here, I did say I was going to show that I don't think I need to do the magnetic dipole moment because look, it's right, I pi r squared is right there. So if these two things agree, these two numbers right here agree, then which they mostly do, then that's fine. So I'm going to plot that. I'm going to plot all 3 of these. So let's make a graph. Let's just do the graph down here. I know this is getting sloppy code, but G1 equals graph, X title equals R in meters, Y title equals B in Tesla. And then let's put the width at 400, height at 200. This just sets the size of the scale. Now I need 3 graphs. I'm going to have Fn for the numerical calculation, G curve color equals color dot blue, label equals numerical, FC G curve color equals color dot green, red, label equals calc, FA equals G curve color equals color dot green, label equals approx. Okay, so now what I'm going to do is I need to start with my R value. Let's start with R03. I'm reusing variables. That's fine. At 0.03. And then dr is going to be how far do I want to move along that axis? So let's say 0.001. I don't know. So while R03 is less than 0.05. I'm just making up something. So the first thing I want to do is to calculate the magnetic field due to the loop numerically. So I'll say Bn equals B vector R03 0, 0. Remember that function I have to pass in a function. And then I need to calculate BA and BC, which I'm just going to copy up here. I don't want to print, so I'm going to delete that. Tab. And this one I need to change this to R03. And this one I need to change to R03. And now I'm going to plot them. So I'm going to plot Fn.plot. I'm going to plot the R03. And then I need to plot the magnitude. I could plot the x component of Bn or the magnitude. I'm just going to plot the magnitude of Bn. And then Fc.plot is going to be R03 BC. That one's a scalar value. And then Fa.plot R03 BA. Almost made a big mistake right here. R03 equals R03 plus dr. Otherwise, I put it in an infinite loop, and that's just freaking embarrassing. I'm going to save this because if I did make a mistake, which is always possible, very possible. Okay, let's run this. Okay, look at that. So here's my plot. You can see that the approximate value starts getting better once you get it, pretty far away. But the other two, they're right on top of each other. They are right on top of the numerical and the calculator, right on top of each other. My numerical calculation here is super awesome. And I just want to reiterate what is so great about this numerical calculation. If you want to do the analytical version for the magnetic field right there, good luck with that. Okay, that is a very difficult thing to calculate. But numerically, it's not so bad. Now, we could do something. I think I'll save this for later. Use this magnetic field to find the magnetic force on another ring. That's really what I want to do. But I'll save that for later videos. So, reminder, I'm giving you the code, link down below. Playlist for the rest of the stuff down below. If there's one of the videos, like I need to find the video for lists. I need to find the video for functions. I need to find the video for an analytical calculation of the magnetic field due to ring. Just leave a comment down below, and I'll make sure I add that. I'll reply to your comment or whatever. I do have those videos. But that's that. Okay, I'm leaving.